We present Omnidata, a pipeline to make steerable multitask mid-level vision datasets from 3D scans. Most existing vision datasets capture images once, locking in design choices and biases that affect resulting models' ability to generalize in novel situations. These static datasets contain object annotations for a specific and limited number of viewpoints. For example, viewpoint distribution is biased based on object category among Pascal images. There are very few images with side view of a sofa. Lots of other papers have also found that these datasets encode all types of hard-to-control biases, such as photographer's bias, selection bias, and so on. This will lead to poor generalization of a model to novel situations, in this case to an unseen camera viewpoint. By controlling all aspects of data sampling, we can study their effects, leading to better research and better datasets. For instance, camera intrinsics such as field of view is an important parameter to consider, and you can see how sampling this parameter from different ranges of the distribution can affect the generated images. Camera distance to the point of focus can also control the level of focus on objects, useful to create object-centric or scene-centric datasets. In contrast to gathering images from the environment with unknown and unchangeable collection parameters, we instead propose to create steerable datasets by using 3D scans and controlling the parameters such as camera poses, mid-level domains, object centeredness, and so on. As we'll show later, the pipeline can create datasets capable of training strong models with more generalization to real world. It provides a pathway to study different data sampling effects by offering a control over dataset design choices. It allows us to do match pair analysis. For example, what causes an ImageNet pre-trained model to transfer better to other downstream tasks compared to alternatives, such as a depth model trained on NYU? And finally, as 3D sensors are becoming more common and 3D scans more available, the pipeline can convert these sources of data to large annotated 3D datasets. But how does our pipeline work? The annotator takes as input either a textured mesh, a mesh with images from an actual camera, or a point cloud with aligned RGB images. It samples cameras to densely cover the space and finally generates a multitask dataset with 21 different mid-level cues per image. The generation and rendering process can be outlined in 4 main steps, which I'll describe in more detail. First, we take a 3D mesh as input. We generate the camera viewpoints if they are not provided to densely cover the space. Points of interest are also densely sampled inside the building. These are the focus points where the cameras are fixated on. We can then generate static images by saving fixated views, and also videos by interpolating along a path. As the final step, we render 21 standard mid-level vision tasks for each generated view. Here you can see 2 trajectories sampled in a replica building with the 5 mid-level cues generated per each frame. As a demonstration, we use our pipeline to create a starter dataset of mid-level annotations from some existing 3D datasets. It contains more than 14 million images from over 2,000 spaces, which covers very diverse scenes and views. Of course, you can use the pipeline to annotate more datasets for your particular use case, such as car law for driving. Now we show that the steerable datasets generated by our pipeline are capable of training very strong models which outperform state-of-the-art in several vision tasks. In depth estimation, our DPT-based models outperform DPT models from Midas V3 on NYU and OASIS datasets. It better recovers the fine-grained details and better reflects the curvature and true shape of the objects as shown by the extracted surface normals. We examine the dataset's generalization and stability in real world by doing zero-shot surface normal estimation on OASIS. You can see a comparison of our model to the one trained on taxonomy dataset. We clearly outperformed the model trained on OASIS data itself and achieved human-level performance according to one of the metrics. Please see the paper for the quantitative results. Complete control over the data generation process allows us to do things that are beyond the reach of most existing setups. For instance, we show in the paper that using mid-level cues as input can improve the performance in other tasks such as panoptic segmentation. We can do 3D data augmentation such as 3D image refocusing using the full scene geometry available in the generated dataset. Here's the result of our model on a random YouTube clip. Make sure to check our website for full details, code, and more results. You can use our online demo to run our pre-trained models on your own images and investigate different data generation parameters using our online dataset explorer. Thanks.